Don't forget we need to put
We are the Auburn University Rocketry Association. My name is James Cannon and I'm the Chief Engineer.
I'm Nir Patel, I'm the President of the Rocketry Association, and this is our submission for the Argonia Cup video.
Our vehicle this year, of course, is two stages. Our booster stage, Bada Boom, flies on a K1000 motor, and our sustainer, Bada Bang, flies on a K455.
Our expected score is approximately 20,000 points.
Hi, I'm Elizabeth Bonema, and I'm the recovery lead for the Argonia vehicle. So we have two avionics bays dedicated to recovery in the vehicle, one in the booster and one in the sustainer. This is the one that goes in the booster. It has two Altus Metrum Easy Minis and sits inside the booster right there with the key switches accessible from the outside. This is the avionics bay that goes in the sustainer. There's also two Altus Metrum Easy Minis on here. This sits inside this coupler and also has two key switches. There are two key switches secured to the outside of the coupler, so the altimeters can be turned on from outside the vehicle. For the booster, the main parachute is deployed at apogee around 3,000 feet. For the sustainer, there is a drogue and a main parachute. The drogue parachute is deployed at apogee and the main parachute is deployed at 650 feet. All of the recovery systems have redundant charges, so if the first altimeter malfunctions, it does not eject the parachute, the redundant charge will. All of our parachutes are manufactured in-house. We do drag calculations to size them, create the patterns in the specific shape we want, cut them out, and sew them in our medians. The parachutes are made out of ripstop nylon. The shroud lines are made of paracord, and the shock cords are 5/8 inch tubular nylon. The booster descends at around 30 feet per second. Under drogue, sustainer descends at around 95 feet per second, and under main, sustainer descends at 25 feet per second.
I'm Tatum Black. I'm a junior in aerospace engineering, and I'm the ignition and separation lead for the Argonia Cup competition rocket. For our logic, we're using two easy timers in the beaker up position. We have them so that they cannot exceed a tilt angle of 20 degrees. They have to be more than 200 feet per second. They are connected to 9-volt batteries, just like the other bays that we have in this vehicle. It is housed in its own bay above the motor in the sustainer, and we have raceway tubes in the motor housing that run all the way down, and it connects to two low voltage igniters as well as Pyrex pellets into the motor itself to ensure ignition. We are using drag separation. We will be utilizing drag separation at 800 feet, which should be 3.5 seconds after launch. This is the bracket that I'm using, and it has two systems for redundancy purposes, both in the beaker up position.
My name is Chandler Livingston. I'm a junior in aerospace engineering, and I'm the payload lead for the Argonia Cup competition. This year, we are placing 11 golf balls within the nose cone of the rocket. This bracket holds 10 golf balls, with an additional one placed in the tip of the nose cone. This is slid inside the nose cone and retained using set screws around the bottom of the nose cone shoulder. And these eye bolts are used for connection to the main parachute shock cords. Additionally, on this bracket, we have mounted a GPS tracking system that we have developed. This system has been used in some previous test launches. We're moving to this integrated surface mount PCB to resolve vehicle integration issues and to save overall space. It is using a Raspberry Pi Pico as the microcontroller and is transmitting over the 915 megahertz band. This is our receiving ground station, which displays GPS latitude and longitude on the LCD display. Our GPS ground station is known as the Intendinator.
Hello, my name is Henry Fowler. I am the Argonia Structures Lead. I'm a sophomore studying mechanical engineering, and I'm here to talk about how we built bada bing, bada boom. The booster and sustainer are manufactured out of fiberglass, which we use doing a wet fiberglass layup by rolling fiberglass onto a mandrel and then taking off and cutting the tubes down to length. The rocket is supposed to reach an altitude of about 14,000 feet, with the booster section only having an altitude of about 3,000 feet. We'll have a maximum velocity of Mach 0.96, and we'll have an off-road velocity of about 78 feet per second. The sustainer and the booster are two different diameters, so to make sure that it can line up on the rail straight, we made a flyaway rail guide. It works by having rubber bands on the back to pull it apart once the rocket leaves the rail. In our test flight, we had really good success with this, with 100% success rate from the rail guide and the booster. The fins and flat plates were 100% manufactured in-house by using carbon fiber and fiberglass flat plates, and we have a 3D printed transition to have the whole vehicle sit together.